So, we have learned about the
Yo, Mr. V's the GOAT.
particle properties of the light.
It nurtured me to be this.
So we learn about particle properties of the light. The light can behave not only as a wave, but also it can behave as a beam of particles. But then we discovered that particles can behave as a wave. And the interesting thing that electron was discovered by English physicist J.J. Thomson, and he was awarded Nobel Prize for discovery of the electron. But later on, his son, G.P. Thomson, discovered that electrons can behave as a wave. So it can be not as a particle, can be as a wave. He was awarded Nobel Prize for that as well. So,
Wait, did they both get Nobel Prizes?
Yes,
they both, yeah, father and son. Father discovered the electron, and son discovered that the electron
Generation.
can behave as a can behave. I don't know. So,
Yeah, okay.
so first, before we will look into his discovery, let's consider if he sent X-rays, which is electromagnetic wave, and wavelength is approximately 10 negative 10 meters on the thin foil, metal foil.
for this topic?
The wave properties of metal. Wave properties, as I said, we'll look into the wave properties of the metal. We learn about the particle properties of the light, so we look into the wave properties of the metal. So, if you send through the thin foil, metal foil, beam of X-rays, and we put behind that foil, we put a screen, and we will have that screen we can see where those X-rays come in. And we will found that diffraction happened and interference pattern was created on the screen. And that interference pattern was used as a circle. The bright in the middle, then dark, then bright, then again dark, which is typical interference pattern.
Does the wave go through like a hole?
No.
Is the wave perfectly like pointed at the center? Is the X-rays?
There is a foil,
Yeah.
the X-rays coming,
Yeah, I understand.
and you
But
have a screen.
What I'm saying is the X-ray, whatever's sending the X-rays, pointing it at the center?
Yeah.
Okay.
Now, why do you think the picture looks like this? Not like we have with a double slit or single slit experiments when we have a bands. Why we have a circles? Why we
Longitude.
have interference pattern in a circles? Sending it through the foil, that's a hint.
Conductive.
How foil is a solid? So what the structure of solid? It has
Electron shells.
atoms, no? Photon has atoms.
Like very close.
And what acts as the slits on which diffraction
The
happens?
space between the atoms.
Spacing between the atoms. Spacing between the atoms.
I mean, there's going to be a
And
lot of
the
difference.
spacing between the atoms is about of this. So we will have as wavelengths of the X-rays and spacing between atoms is similar in size, the diffraction happens. And why interference pattern happens? Because we have here, we have slits, both vertical slits and we have a horizontal slits. And we have vertical slits will produce vertical, producing vertical bands, horizontal, producing horizontal, and as a result of addition of them, we get a circles. Because we have interference in 2 dimensions. We have diffraction in 2 dimensions. They diffract horizontally and vertically.
Wait, I'm confused. What's
Yes.
like the setup for like this thing? Like,
Is the
Hey,
screen...
Diffraction of X-rays on the metal foil.
Is the screen there and the foil right on it, or like is it far away from it?
not far away at some distance.
But it's away from the screen. But
Yeah,
how does the X-rays get through? It can go through foil.
if it's thin
It
foil,
can go through.
very thin foil, like close to 1 atom thick.
Ah, okay. Oh, so very thin.
So yeah, very thin foil. So we have the spacing between the atoms act as the slits. But because we have horizontal and vertical slits, those diffraction adds up, and we got those circles. And then G.P. Thomson did his experiment. He sent a beam of electrons on the foil. And there was a screen behind which, when electron hit that screen, the so-called scintillations happen, so it starts like producing light. It becomes bright point. Where electron hit the screen, there was a bright point. And it was amazing that the beam electrons made on the screen same pattern as X-rays. And this is the interference pattern. And only waves can create interference pattern. So what conclusion we can make? That electrons behave as a wave. So everything has dual nature. Particle, not only light can behave as a wave as a particle, particles can behave as particles and the waves. Now let's put some calculations, some numbers into that, how we can do any calculation. And what are the wavelengths of the beam of the particle? Is determined by the momentum. It's determined by the momentum of the particles. P equals mv. And the wavelengths equal Planck's constant. In this case, must be in joules per second, not electron volts, over momentum. That was de Broglie's hypothesis. Now, this way it came from, we will discuss a little bit later on, that came from the, when we will talk about the energy levels of the atoms, to display the spectrum of the of hydrogen, and that's where those energy levels were pretty much of the atoms discovered, and to make this what was coming from the explanation of those energy levels, which we will learn a little bit later on, not today. From that came. So that's not come like de Broglie, who suggested, made this hypothesis, not like he looked on the ceiling and said, let's wavelengths will be equal Planck's constant divided by momentum. It came on the analyzing of the results of the hydrogen spectrum. But we will discuss it later on, but that's where it's coming from. So it's not on the like from nowhere.
You solve path difference. You find out.
And yes, so we'll talk about the path difference later on. Why we don't observe any wave behavior of the particle in our lives? Let's calculate momentum. Let's say,
Because the mass is so high.
let's calculate momentum. Let's say ball with a mass, let's say 0.5 kilogram, and moving with a speed, well, let's say 20 meters per second. So what will be its momentum? P will be equal 10 Newton seconds. Let's calculate what will be the wavelength of this ball. Wavelength equals 6.63 10 negative 34 divided by 10, so equals 6.63 times 10 in the negative 35 meter. Can such small wavelengths be detected? No, it's too small. That's why we don't see wave properties of the matter in our everyday life.
Is that similar to gamma? Like closer to gamma or infrared?
Gamma has frequency has wavelengths much longer than that. Like probably, can I tell from top of my head, the gamma will be something like 10 negative 12,
So what's
10
something?
negative 13.
What's something similar to that?
Nothing.
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 So gamma, can you detect
Right.
gamma?
Gamma radiation, yes, we can detect gamma.
So gamma is like the smallest wavelength we can detect.
Yes. So yes.
So with the whole like particles can act like a like, could you like, does that relate at all to like planets that would have like a lot of momentum and they're kind of
Sorry.
like planets like in space like
Yeah.
like
But they have
like,
huge momentum.
yeah.
So their wavelengths will be even much smaller than that. It's
Right.
not detectable.
Oh, okay.
So if you had something of like, say, not much mass moving
Oh.
extremely slowly, so the momentum was very low, it would have a higher wavelength.
Like-
Yes,
like-
and then let's calculate.
Wait, is this like quantum physics? Is this like...
Yes, that's the basics of the quantum physics. Let's calculate the wavelengths of the electrons. Let's
Like,
calculate
how
wavelength
much
of the
energy is
electron.
like-
Mass of the electrons is
You learn in
9.1
uni.
times 10 in the negative 31 kilogram. So let's say electron moving 1000 meters per second. So its momentum will be 9.1 times 10 in the negative 28 Newton seconds. So we substitute here 6.63 times 10 negative 34 divided by
Right,
9.1
that's like the wavelength of visible
times
light.
10 negative 28. So that will be 6.63 divided by 9.1 will be something like around 0.72. You can check with the calculator, please.
Wait, what's the power of? What power are we trying to find?
This
What
is
wavelength are we finding?
of electron.
Okay.
What you got? 0.7,
It's like 7.29 times.
say 0.72. So 7.2 times 10
to the
negative 10
7.
negative 7. Which is 720 nanometers.
That's visible.
That will be visible light.
That's like red.
So for small particle in the microwave, the wavelength becomes detectable. But usually electrons moving faster than that, so wavelength is shorter and compatible to the wavelength of the X-rays. Now, very important thing, and what we will have problems when we have, it will say the same or similar pattern obtained from X-rays and from the electron coming through the foil. What is necessary to have, what will be the condition to have the same
Same
interference?
velocity. Is it velocity?
Same wavelength.
Oh.
So we'll consider here photons,
Is it the same velocity? though?
the
They have the same momentum.
X-rays. Sorry, what you
It's
said?
the same
Ah,
velocity.
what- what you said, same? Same momentum. What you said before? Energy?
Energy?
Did you say energy?
Sure, he said it.
Yeah, I said energy.
Energy. And you'll find that it will be very different. You'll find
Because they can have
same
different
momentum, but very
They
different.
have
So
different masses.
photon X-rays and we have electrons. And we found that wavelengths of X-rays equal wavelengths of electrons. That is necessary to have the same interference pattern. As they have same wavelengths, they will have same momentum. So momentum of photons of X-rays equals momentum of electrons. Let's find their energy. What the formula for energy of the photon? HF or HC over wavelength. And H, Planck's constant over wavelength, is momentum. So we will have the energy of the photons of X-ray equal P times C. So this equals momentum. So momentum times speed of light. energy of the electron is kinetic energy, mv squared on 2. Now we have what will be if you rearrange kinetic energy in terms of the momentum. Momentum equal mv, P equal mv, E equal mv squared, so what will be energy? If it's square momentum,
M squared V squared.
so that will be P squared over 2m. If it's square momentum, P squared equals m squared V squared, and substitute that, we'll get energy equal P squared over 2m. So that is energy.
Why 2m? I understand why p squared.
Because we have 2 here.
But why does m go down?
From here, we need substitute
Yeah,
here
what do you
mv
substitute?
squared.
Substitute.
From here, mv squared
Equals.
equal what
P
mv
squared.
squared equal P squared over m.
Wait, I'm looking at the top. Top p equals mv.
Then we square both of sides. P squared equal m squared v
Wait,
squared.
why did you square both sides then?
So
If we want mv squared, we need square.
Can't you just do p squared though?
Yeah, P squared equals m squared v squared.
Also, P
We
squared.
need here get momentum. So we have relation that kinetic formula for kinetic energy of electrons P squared
I'm still
over
confused.
2m.
Can't you just do p squared on 2?
It's P squared will be m squared v squared. We don't have m squared here. There is not m.
Ah, it's just v squared.
Yes,
Yeah.
that's why it will be this.
Because when I look at the squared, I think m is squared as well, and v is squared. If there were brackets, you could just do it.
So, if they have same momentum, now let's find the ratio of the energy of the photon divided by energy of the probably let's do calculate momentum of the photon with the wavelength of 1 times 10 negative 10. So let's calculate what will be the momentum if wavelengths equal 1 times 10 negative 10 meter, typical wavelengths of the X-rays. So what will be the momentum? We have Planck's constant divided by wavelengths will be equal 6.63 times 10 negative 34 divided by 10 negative 10, and we get momentum equal 6.63
times by 3 from
times 10 negative 24.
You
I'm-
can times
And I'm finding the
the
momentum of the X-rays with the wavelengths of 10 negative 10 meter. Yes,
Why do we have to take h in joule seconds?
because momentum measured in Newton seconds.
Oh,
So
that's where you get the
kilograms,
seconds from.
kilograms, meters, seconds, that's where joules is. Electron volts
Is voltage.
is, no, not volts, it's unit of energy, but when they can kilogram, it's not involved kilograms.
Yeah.
Yes.
So if we say we were trying to figure out something that is like going back to like stopping voltage and stuff like that.
No, we can use both electron volts
Yeah.
and joules. Electron volts is just much more convenient.
Yeah.
But we cannot use electron volts here because electron volt, if you find the dimensions of electron volts, it will not be kilogram meters
Yeah.
per second.
Okay.
So let's find the energy
Yeah.
of this photon. Energy of this photon. Energy equal momentum times speed of light. So equal 6.63 times 10 negative 24 and times 3 times 10 in the power of 8 speed of light. What we will get if we multiply that will be 1.10, 1.9, 8 will be about approximately 2 will be 2 times 10 in 10 in negative 15. Can you please check my calculation with the
That's
calculator?
about right. Like 1.99.
Yeah. 2 times 10 negative 15 joules.
Yeah, it's 1.989. So
Yeah.
1.9.
Now, let's calculate that the energy of the photon of X-ray. Let's calculate what will be the energy of electron to have the same wavelength, so same momentum. So energy will be equal P squared, this is a momentum, so 6.63 times 10 negative 24 squared divided by 2 times mass of electron, 9.1 times 10 negative 31 will be equal, that will be something approximately, something like, I will estimate something like 2.2 times 48 minus 31.7 negative 17, something like that.
It's
Can you
2.42.
2.4?
Yeah, 2.42.
Okay, 2.4 times 10 negative 17 joules.
Yeah.
So, for having same momentum, but energy of the X-ray photon about 100 times need to be greater than energy of the electron to have same momentum. Because photon does not have mass, an electron has mass.
Aren't you just finding the energy, the kinetic
We're finding the energy of photon
of
and
photon?
electron with the same momentum and so same wavelength
as an X-ray?
as X-ray. Yes.
Is
Ah.
kinetic energy equal to momentum squared divided by 2m true in like all cases?
Sorry, I had to P squared
Yeah,
over 2m.
that's-
It's applicable always.
Everywhere, okay.
It's everywhere. It's not just for electrons.
So wait, do we know the energy of an X-ray? What
We
do you?
calculated it from the
Right.
wavelengths. We know its wavelength. You say that we take wavelengths,
Yeah.
and so to have the same diffraction pattern of interference pattern, the electron must have the same wavelength as the photon of X-ray.
Yeah, but why is the energy different?
Because electron has mass, and
Ah,
photon does not.
Okay, right.
That's why to have same momentum, it must have 100 times more energy.
Does that mean
Why?
that is equal to HF minus water, or only when?
No, it's not.
This
It
is
has nothing.
This
to-
is when it's acting as a wave. That's when it's acting as a particle.
No, it is momentum. Can we talk about the momentum of wave? No. So this is when we have photon acting as a particle.
Where then?
And we discussed that light exerts force. Remember we were calculating force. So if we have beam of
But isn't are we
X-rays,
doing an electron acting as a wave?
sorry?
Isn't this an electron acting as a wave?
Yeah, it's acting as a wave, yes.
Because
And they make, this is where it's coming, they both
What?
waves, the light, or X-rays the light, and electron, they both have both particle properties, wave and particles.
Well, shouldn't
At
the
the same
energy
time.
for an X-ray then be zero? Because
If its
zero,
energy will be zero, then
because
it doesn't have any frequency,
It has
and
no
it's not
mass, though.
X-ray.
No, but A equals HF is what.
Energy of the photon is Planck's constant times frequency.
yeah, but
That's what we
but
get
if
from
you-
the photoelectric
if you
effect.
find the energy, kinetic energy through that formula, E.
But you don't
equals
use this
V
formula when it's
squared.
acting.
We
as a
know
wave.
this formula not applicable for photon.
Ah, okay.
It's applicable only for something that has mass for
That's-
electron. Yes.
How does an electron create an interference pattern?
Because it's behaved as a wave.
So is it like passing through something?
It's
Yeah, the
very
foil.
It passing through the. It was passing beams. We have a made of
Through the
foil,
foil,
thin
yeah.
foil, and we have beam of we have X-rays coming through the foil and creating interference pattern.
Is it?
But then we send the beam of electrons, and on the screen where electron hit the screen, we can see it.
Okay.
and they made the same interference pattern.
Is it only through foil that that happens? Like, would it happen in like a double slit or
It
something?
will happen, yes.
So if you pass electrons through, like,
Beam of
two-
electron through two slits, we will get bands on the screen.
And is that the same pattern with like the bright bands are our wavelength apart?
Yes, yes, it's the same thing. The path difference determine that, but the thing is, in this area of study, you will not have to calculate path difference. You will have to calculate momentums, energies, wavelengths, but not the path differences.
And what's the is it an electron in the foil that makes the slits? What makes the slits in that?
In the foil, atoms
Atoms.
that made the crystal lattice.
What's the difference between an atom and an electron?
Electrons in it.
Electrons in an atom. Yeah.
Electron
okay.
consists
Oh,
from,
atom.
it's a good question from your 12 physics student. What is the difference between electron and atom? Maybe we need to go back to grade
I need to go back to
think,
grade
yeah,
2.
9. Oh, okay.
8, maybe.
8.
Yeah.
Yes.
So,
I don't know.
Would-
That's what last year was.
do all physical particles have wave properties?
Yes.
If given the correct momentum.
Yes.
So,
But for any object with a significant mass, with the smallest velocity, still momentum will be too huge. So we can observe wave properties only with the subatomic particles.
so like protons and neutrons.
We can observe wave properties of protons, neutrons. Yes. we
What about
can.
atoms?
Atoms?
Is there like
Of the light atoms, yes. Heavy atoms, no. Probably
You're not
bigger than
putting uranium.
where,
through.
yeah, because it will be too big mass and too short wavelengths. But for light atoms, yes, we can.
Do they have to have momentum to observe?
If something not moving, it does not, excellent question, it does not exhibit any wave properties. If velocity is zero, momentum is zero, and so there is no wavelength.
Wait, can you have a wavelength of 0?
So when it has a mass, it acts
If
as
we
a
have,
wave.
we have that wavelengths equal h over p. If
Yes.
speed is zero, momentum is zero, what will be wavelengths?
Undefined.
Infinity, and therefore undefined.
How do photons act as a wave if they don't have mass?
Photons will act, sorry, as a wave of particle.
As a particle.
As a particle, and that is,
doesn't have
yeah, it's very strange. They
Zero,
don't
just
have,
like that.
but they can exert force. When they hit the ball, that exert force on the ball, even if they don't have a mass. Another interesting thing, if you think about the black hole, the light doesn't have mass. So law of the gravity shouldn't be applicable, but if light coming close enough to the black hole, it bends, which probably can be explained that the black hole actually curved in the space, and that's why light is curved, but it does not have mass. And I think that's enough for today. New material. There is one bit that I cannot explain today. It was related to your question that you asked me earlier about how we know how electrons going through, let's say, through the slits, where it's going. And that the principle, Heisenberg's uncertainty principle tells us, but I will leave it to next lesson. Okay, that's all
Is it Heisenberg's uncertainty?
for today.
Principle something like
Like, subscribe, and donate to help to beat those Russian fascists.